Hello students, in this particular lecture we will take a look at the skewed gates. So previously we had seen the asymmetric gates and how do we evaluate the logical effort for the asymmetric gates. So today in this particular lecture we will look into the skewed part of the gates. Please note that skewing is not equivalent to the asymmetric gates. Asymmetric gates means the input capacitance seen by the several inputs are different. So if I have two inputs to the particular gate, and if their widths are designed in such a way that their input capacitance for the several of the inputs, if they are different, then it is called as an asymmetric gates. Whereas the skewed gates, even though the inputs might see the same capacitance based on the designs whatever we have, the skewing happens with respect to the pull-up circuit and pull-down circuit. Right, so in that sense, for an inverter, and if I say that it is a high skew, that means that the PMOS is more dominant with respect to the NMOS. So what it indirectly also means that the PMOS has a better width, so the better current driving strength than that of the NMOS. Right, and similarly, a low skew inverter will resemble the inverter having or dominated by the NMOS transistors and not by the PMOS transistors. All right. So here is our usual inverter, a primitive circuit. This is the size of the PMOS transistor is 2 here, and then the size of the NMOS transistor is 2 here, and it is not 2:1, right? So what it really means is it is a skewed inverter. And if I have a skewed inverter, how do I find out the logical efforts, right? And how do I find out the parasitic, the normalized parasitic that is seen at the output node? So what we had been saying is, while we set up a benchmark inverter, right, for any gate, if I want to find out the logical effort or the normalized parasitic delay, we set aside a benchmark inverter. And we used to say that the benchmark inverter's current should be same as that of this particular gate's, the current. In this particular case, because it is a skewed inverter, the current strength of the PMOS will be different than that of the current strength of the NMOS. Now, one can always say that both of them are in series. So what is that current strength? Because all the series transistors are eventually likely to pass the same current here. But what I really meant was, if I'm trying to, if I have a capacitance here at the output node, this particular capacitance charging current, right, will be different than that of the capacitance discharging current, because the driving strength or the width here, which has been designed for the particular transistors, are different, right? So in that sense, although the widths are same here in this particular case, the betas of the PMOS and then the NMOS are different, and that's why the current strength, the current value will be different, right? So in that sense, what we are saying is the output current in this particular node, while it is charging through the PMOS, that particular current will be different than when the capacitor is actually discharging through the NMOS. So now the question is, if I want to evaluate the logical effort or the normalized parasitic delay factor, now what should be the benchmark inverter? The benchmark inverter should be designed in such a way that we should have a benchmark inverter in such a way that its current, the rising current, should be the rising current whatever this particular gate will give, and then its falling current will be whatever this particular gate will give. So for example, if I want to find a benchmark inverter so that I can evaluate the logical effort, the benchmark inverter for the falling current should give me a current of 2i. And the reason is because this NMOS here, it is size to 2, that means the current strength will be 2, or rather the falling resistance is R by 2. And I'll get a current strength of 2i or the falling resistance to be R by 2 only if I have a benchmark inverter with an NMOS size of 2, and the benchmark inverter should always have the equal betas, right? So what I mean is the benchmark inverter should always be in a ratio of 2:1 or 4:2 or 8:4 and so on, right? So in that sense, if I'm making this 2 size here so that I'll get the falling current as 2i so as to match with that of this gate's NMOS transistor size of 2, my PMOS size of the benchmark inverter will be twice that of the size of the NMOS transistor here. So it should be 4 here. So I will now have the benchmark inverter of 4:2. Similarly, if I want to find out the benchmark inverter for the rising current, so the rising current or the charging current is nothing but I here, because the size of 2 in the PMOS side will give me a current of 1I. So I need the same charging or the rising current in my benchmark inverter. So I need to have a size of 2:1, which will give me the rising current of I here in the benchmark inverter. So hope this is clear. So what we now have is two benchmark inverters, one for the rising output and another for the falling output. So one for the rising output, this is the benchmark inverter, and then one for the falling output. So if I have two benchmark inverters, I cannot get one logical efforts, right? So in that sense, I will have two logical efforts defined now. So the logical efforts for the output going up, and then the logical effort for the output going down. So it is represented as GU and GD. And GU will be nothing but, so if I consider the input capacitance of this particular gate, it will be nothing but 2 plus 2. So 4C divided by my benchmark inverter's input capacitance, which will be 2 plus 1, which will be 3. So my logical effort for the rising output or the going up output will be 4 by 3. And my parasitics for the rising output will be nothing but, the 4C seen at the output node, and then the 3C seen in this output node of the benchmark inverter of 2:1. So I will have the PU value parasitic for going up will be nothing but 4C divided by 3C, which will be nothing but 4 by 3. Similarly, for the logical effort for going down will be nothing but 4C divided by 4 plus 2, that is 6C, so it will be 2 by 3. And the parasitics for going down will be again 4 divided by 4 plus 2, which will be nothing but 2 by 3. So hope this is clear. Moving ahead, so kind of an empty slide. So I'll try to derive the benchmark inverters for this particular Hi-Skew inverter. So let me pick up a pointer. So this is an Hi-Skew network. So I have a VDD rail here, and then the PMOS transistor, and then the NMOS transistor. The PMOS transistor has a size of 2, and then the NMOS has a size of 0.5. So which means my beta P is actually higher than that of the beta N, and that's why it is called as an Hi-Skew inverter. All right. Now, how do I find out the logical efforts and then the parasitics, which has a different sizes? The PMOS and NMOS has a different sizes. So I need to draw two benchmark inverters again, one for the rising output and another one for the falling output. Right. So in that sense, I will try to draw the benchmark inverter. The benchmark inverter should give me the rising current here will be nothing but I. Here the falling current is nothing but 0.5I. Here the rising current is nothing but I. So for my benchmark inverter, it should be nothing but the size of 2:1. So I will draw my benchmark inverter with a size of 2:1, which will give me a rising current of which will give me a rising current of I, and then the falling current of I. And similarly for 0.5 width, my benchmark inverters. So this will be my inverter here, and then it's connected to another inverter. So my the size of this particular benchmark inverter should give me 0.5 as the current. So I'll have 0.5 as the size here, and then it should be the size of 1. So 2:1 ratio is maintained in the benchmark inverter. So this will give me the falling current of 0.5I and the rising current of 0.5I. So my benchmark inverters are ready now, and now I need to evaluate what should be the logical effort for the going up, and then logical effort for the going down signal, right? The output signal. So the logical effort for going up will be nothing but 2 plus 0.5. At the input, it sees 2.5 capacitance divided by the benchmark inverter of 2 plus 1. So which will be nothing but 3. So overall, I'm going to get 5 by 6. Its parasitics for going up will be nothing but the same, 5 by 6. Logical effort for going down signal is nothing but 2 plus 0.5. Right? 2 plus 0.5 divided by 1 plus 0.5, which is nothing but 5 by 3. And the parasitic for going down will again be nothing but 5 by 3. All right, so this is how we will evaluate the logical effort and then the parasitics. It's a very interesting thing here is the logical effort turns out to be less than 1. 5 by 6 is actually less than 1 for especially for the one which is the rising one. All right, the going down, it is kind of compensated by the going down the logical effort, so it has a very high the logical effort. All right, and similarly we can see the parasitics is 5 by 6 here, less than 1, which is the normal case for the 2:1 inverter. We will have a parasitics of 1, but here because of the skewing technique, this parasitics for the going up is less than 1, and parasitic for going down is being compensated by 5 by 3. Right, so with a higher skew, that means the PMOS is more dominant. It is likely, right? So it is likely that the output will be pulled up, and that's the reason we will have a lower logical effort and then the parasitic normalized parasitic delay factor. Right, so a higher skew will always be associated with a lower value of GU and a lower value of PU. A lower skew inverter, that means the NMOS is kind of dominated. That means the circuit pulls down the output efficiently. In that sense, the logical effort for the going down, so the GD and then the parasitic normalized parasitic delay, the PD for the going down will be less if it is a low skew inverter. Hope this is clear. Moving ahead. So in this particular, I have drawn a series of circuits starting with the unskewed inverter. Unskewed inverter, we anyways know the GU, GD and G average is nothing but the same value as 1. Parasitic is also all the parasitic for going up, going down, and average value is 1. Hi-Skew, we recently, in the last slide, we just had a look at it. So it is 5 by 6 for going up, and then the GD value is nothing but 5 by 3. Average turns out to be 5 by 4, so it is kind of slightly higher than that of 1 of the unskewed inverter. Parasitics is nothing but 5 by 6, 5 by 3 and 5 by 4, very, very similar to that of the logical efforts. For the low skew, having 1 and 1 here, that means that the NMOS beta here is more than that of the beta of the PMOS. Right, although the width is same, this one is called as a low skew because the beta of this NMOS transistor is higher than the beta of the PMOS. Right, and suppose if I have this and this, so my benchmark inverter for this circuit will be 1:0.5, so 1 on the PMOS side and then 0.5 on the NMOS side. And similarly for this, the benchmark inverter will be nothing but 2:1. So I'm going to write it as the benchmark inverter or inverter here just to ensure that we know what we are talking about. So the logical effort for going up will be nothing but 2 divided by 1 plus 0.5, and for the PU, the parasitics for going up will be nothing but 2 divided by 1.5, which will be nothing but 4 by 3 and 4 by 3. GD, the logical effort for going down, will be seeing a different benchmark inverter, which will be 2:1 inverter. So its logical effort for going down will be 1 plus 1 divided by 2 plus 1, which will be 3, so 2 by 3. And the parasitics will be 2 by 3. The average of this turns out to be 1 and 1. All right, so because it's a low skew, the GD value is less than 1, the PD value is less than 1. As we had seen for the high skew, the GU value and then the PU value is less than 1. But however, it is kind of compensated for the other side, right? So for the low skew, the logical effort for going up tends to be more, and then the parasitics for going up will also be more than 1. Unskewed inverter, one more unskewed inverter, 1:0.5. It is still called as an unskewed inverter because the betas of the PMOS and NMOS remains the same. And it will be very, very similar. So 1:0.5, the benchmark inverter for both of them will be 1:0.5 inverter. So its GU value, GD value and G average value will stay at 1, and PU, PD and P average value will stay at 1. Again, hope this is clear. Moving ahead, let's take a look at the 2-input NAND gate. So a high skewed 2-input NAND gate is written here. And it is called as an high skewed because if I look closely into this, the equivalent transistor for this two series transistor will be nothing but, so if it is 1 and 1, right, I will have the equivalent transistor for this will be 0.5. Right, the reason is very simple. This one will give me a resistance of R, switching resistance of R. This one will give me a switching resistance of R. So if I want the equivalent resistance, equivalent transistor should have a switching resistance of 2R, and it is possible only if I have 0.5 as the width. All right, so this is my equivalent, the resistance of 0.5. 0.5 with respect to 2, in parallel. So these two are in parallel. So I will have two of them in parallel, size of 2 and 2. So this being, so if one of the branch is on, the other one, under worst case condition, we say that this input is on, or this particular transistor is on, and then this is off. So we'll have 2:0.5. Thereby we have this, the PMOS being more dominant. So that means that the beta of the PMOS is higher than that of the beta of the NMOS. And that's why it is called as an high skew 2-input NAND gate. All right. So now if I want to find out the logical efforts for going up and going down and parasitics for going up and going down, I need to find out the benchmark inverters for the going down signal and going up signal. So the benchmark inverter for the going up signal and then the going down signal, I'm going to rewrite this. So I'm going to draw that. So this will be nothing but 0.5 is the width. So its current for going down should be nothing but 0.5 into I. So what I need is the benchmark inverter of 1:0.5 is my benchmark inverter, which will give me the going down current of 0.5 I. My benchmark inverter for going up signal, which has the current of, if one of the branch is on, it will have a current of I. So my benchmark inverter will be nothing but 2:1. Because it will give me a current of I. So now if I have the benchmark inverters ready, I can easily find out the logical effort of the going up signal. Right, so the going up, logical effort for going up signal will be nothing but 2 + 1, the input capacitance of this particular high skewed gate will be nothing but 3 divided by my benchmark inverters, the input capacitance is 3. Parasitic for going up, right, will be nothing but whatever is the capacitance seen at the output node. So here the capacitance is 1 + 2 + 2, that will be 5, and then divided by the inverter's parasitic 1 will be nothing but 5/3. All right. For going down signal, the logical effort for going down signal, so this will be my benchmark inverter now. So for going down signal, again the input capacitance is 3 divided by 1.5, so it will be nothing but 2. And the parasitics for going down will be nothing but 5, 2 + 2 + 1, which will be seen at the output node, the capacitance seen at the output node, divided by the benchmark inverters, the output capacitance, which will be nothing but 1.5. All right, so this turns out to be 10/3. Hope this is clear for a 2-input NAND gate. So we have two different benchmark inverters. For evaluating the logical effort for the going up signal, we have the benchmark inverter as 2:1. For the logical effort for going down signal, we have the benchmark inverter as 1:0.5. Okay, moving ahead. So for a 2-input NAND gate, I have this unskewed, high skew, and low skew. Unskewed, this is something we already know, 4/3, 4/3, and 4/3. Parasitics is nothing but 2, 2, and 2. For the high skew inverter, which we had seen in the previous slide, it turns out to be 1, 2 for GD is equal to 2, and parasitic is 5/3 and 10/3. So its average value turns out to be 1.5, and the average value on the parasitic turns out to be 2.5. For the low skew inverter, for the low skew 2 input NAND gate, sorry, our sizes are 1 and 1 here and 2 and 2. So that means that this one will give me an equivalent transistor with a width of 1. So because this is R by 2 and then this is R by 2, so the total switching resistance will be R. So a transistor with a size of 1 will give me an equivalent switching resistance of R. On the PMOS side, the width is 1 and 1. The width is 1 and 1. So that means the switching resistance is nothing but 1 R, or rather R 2R. So in that sense, I think this width of 1 is going to have a less beta than that of on the pull down circuit side, right? So its equivalent resistance on the pull down side will be nothing but one single transistor with a size of 1, giving a beta of that NMOS which is higher than this particular beta of this particular PMOS, right? So it's the benchmark inverter for this and this. I'll try to put it in a different color. So the benchmark inverter for this with a size of 1 on the PMOS side, and then so 0.5 on the NMOS side. This particular for the going down signal, the benchmark inverter will be 2:1 because its equivalent transistor size turns out to be 1. So I will have 2:1. So the logical effort for going up is nothing but, so the input capacitance is nothing but 3 divided by the benchmark inverter is 1.5, so it will be 2. Parasitics will be nothing but 1 plus 1 plus 2, so that is 4, and then its output capacitance will be 1.5, so 4 by 1.5, which will be 8 by 3. Logical effort for going down signal, we will have 2 plus 1, that is 3 divided by 3, so that will be 1. And parasitics for going down signal will be nothing but 2 plus 1 plus 1, that will be 4 divided by 2 plus 1, that will be 3. So this is 4 by 3. Average is 2 and the logical effort average is 1.5. So the 2 input NAND gate, if I actually look into the G average value and the P average value, turns out to be actually 1.5 is greater than 1.33. For an unskewed inverter, it is actually 1.33. P average is nothing but 2, which is same as that of the unskewed inverter. The only advantage is in this GD value, which is actually 1, right? And then the PD value, which is nothing but 4 by 3. So if in a circuit, if I have the going output signal, coming from the 2 input NAND gate. So if I have a 2 input NAND gate, and if it is characterized to some extent that we will have a lot of outputs going down, then we can actually resize this. We can actually skew it in such a way that I will have a lesser GD value, lesser PD value than having the regular GD and PD value. So if I have characterized and if I have noticed the circuit or whatever, the digital circuit system where the 2 input NAND gate is going to give me many times going down signal, then why don't we do it a low skew 2 input NAND gate? So that's an advantage. Of course, one has to pay the price. So if it is low skew, on the higher side, whenever the output rises, I will be having a larger delay because my GU value and the PU value is higher. So one has to compensate for the other side. But if it is more number of times the output is going down, then why not have this GD value has to be 1 and PD value has to be 4 by 3.